Okay, so new topic for today. We've been talking about using change of variables, a specific application of change of variables, using coordinate systems as change of variables functions, right? This is kind of a clever idea, and it turns out that it's extremely powerful in allowing you to compute certain kinds of integrals that if you did them in rectangular coordinates, there'd be square roots everywhere. It'd be a nightmare. Right? But if you use spherical coordinates or polar coordinates, something like that, then all of a sudden the integrals become a lot more doable. Okay, so we're actually going to talk about a new kind of integral now. And it's a little bit surprising. We already did 1 dimension, 2 dimensions, 3 dimensions. What else is there to talk about? Right? Are we going to do 4-dimensional integrals? So no, by the way, not that there's anything particularly bad about that, but that's a whole different subject. So what we've been kind of blurring, what we've been sort of sweeping under the rug, is that there's really 2 dimensions involved in each one of the considerations we've talked about, and we're going to consider now where those 2 dimensions aren't equal. So, for example, what if this is a picture of our domain? The 2 dimensions in question are: what dimension does this picture live in? It's a 2-dimensional picture, right? But then separate question, what is the dimension of the domain itself? The domain itself there is it's a curve. It's a really intrinsically 1-dimensional thing that lives in a 2-dimensional world. Right, so what if I wanted to do an integral on that domain? And by the way, now why would I want to do an integral on a domain like this? Maybe to compute its mass, maybe to compute who knows what it might be accumulating over that domain, but might I want to do a chop it up, add it up approach to some question on that domain? Well, sure, of course I might. Right? Again, the obvious one is mass. If I wanted to compute the mass of a something that was bent and twisted around in the plane like that, it's not a double integral. Double integrals are accumulations of mass over area. There's no area here. It's not really a single variable integral. It's certainly not a question we could have answered in a Calc 1 class because, well, the domain is not part of the x-axis. So this is a brand new problem, right? Now, similarly, could have a 1-dimensional domain in a 3-dimensional world, or a 2-dimensional domain, a surface, right, in a 3-dimensional world. We have not considered any of these kinds of questions to this point. Okay, so we have to completely reconsider the question of, what do Riemann sums even look like? And we're going back to definition. This is a brand new kind of integral. This is not a computational tool for computing integrals that we already know how to talk about. That's not what we're doing here. This is not like spherical coordinates or polar coordinates where it's really just a computational tool. These are brand new integrals. So, for example, if you have a curve like this, well, you could very reasonably chop it up into little pieces, etc. And on each little piece, you could talk about what is the size of that little piece. And per the usual chop it up, add it up strategy, we're going to take the size of each little piece, multiply by some integrand for whatever reason. This integrand, depending on what it is that you're computing. If you're computing mass, well, then that's mass per unit length. Right? If maybe there's a bunch of ants crawling around on this wire, and you want to compute the total number of ants, right? Then that's going to be ant population density, ants per inch, right? Ants per unit length, what have you. Okay, so size times some notion of density to give you little pieces of quantity that you then add up over the entire piece, and take a limit again to make round off errors go away as usual. Okay, so there's our Riemann sum strategy. Okay. Likewise, now, by the way, practically identical in 3 dimensions. Here, let me make this a 3-dimensional thing now. Here, there we go. Now it's in 3 dimensions, right? This is now a 3-dimensional picture. Right? Really very much the same thing. The computational details are going to be ever so slightly different, but it's morally the same. Okay, but now what if we have a 2-dimensional domain, like a surface in 3 space? Well, this is going to be a little different, but it's still chop it up, add it up. So it's just that, okay, when you chop up a surface, you don't get little pieces of length anymore. Now you get little pieces of area. And those areas you would plausibly multiply by stuff per unit area, whatever. Now again, it depends. Are we computing mass? Are we computing ants? What are we computing here, right? So quantity per unit size being area, quantity per unit area, a density appropriate to this context. And that, as usual, gives us stuff, and the grand total of all the little pieces of stuff gives us the total amount of stuff. Okay, all right. So these are new kinds of Riemann sums. Now, the burning question, though, how do you compute these things, right? We were very fortunate when we were looking at single variable integrals because we encountered the fundamental theorem of calculus. That's awesome, right? Thus the name. Double integrals, we broke down to being able to compute with single variable integrals, triple integrals, likewise. So what are we going to do with these things, right? And this is a kind of a weird and scary problem. Let's look at one of these domains a little more closely, right? How am I going to chop this up? Am I going to take plane cross sections? Slicing it with a knife that way, and then slicing it again with a knife this way, etc. That seems pretty weird, right? And it's not clear that that's a good strategy. So we're going to take a different approach. This is a really clever idea. We're actually going to borrow an idea that we've been talking about for a while now, right? So before today's lecture, we were talking about integrals in spherical coordinates, polar coordinates, right, which were change of variables. Before that, we were doing change of variables explicitly. We've kind of been doing change of variables for a while now. The big idea behind change of variables was if there's a domain that you don't like, view it as an image of something that you do like, and then do a pullback, right? The big idea of change of variables is pullback. We can't do change of variables exactly in these situations because, well, again, the problem is it's not just that we don't like these domains, it's that they're dimensionally out of place, right? So we have to do something that's going to fix the fact that they're dimensionally out of place. And it turns out the pullback strategy is going to work just fine, right? So here's how that breaks down. Now let's start with a curve. Here's a curve. So this is a domain that's one of these new domains. It's a one-dimensional domain in a two-dimensional world. Oh, how do we deal with this, right? Well, I would like to simply view that as being the image of something that I do like. And now, what is it that I like so much about this over here? This is an interval on the t-axis. Why do I like that interval on the t-axis? Because it's dimensionally where it belongs, if you will, right? So it's a one-dimensional interval in a one-dimensional world. It's not dimensionally out of place. So if I can view my curve, one-dimensional thing in a two-dimensional world, if I can view my undesirable curve as the image of a perfectly acceptable interval, and if I can do a pullback, then we win, right? Because we're really good at doing integrals on intervals. All right. So now, big observation, of course. This goal that I've now set for myself. I would like to view a curve as being an image from the t-axis. We already know how to do that. That's parametric curve. That's an old idea, right? So that's really good fortune. So part of the tool that I need to do this, this aggressive idea of, let's try to compute an integral over a curve dimensionally out of place in two dimensions by pulling back after having viewed it as an image. That's kind of an aggressive idea, and the big tool is already there. Okay. Parametric curve. So, in fact, some of the algebraic development that we need is already there. Let me just remind you, if you have a curve, and if you're focusing your attention on a little piece of that curve, And by the way, this is just a blown up, expanded version. I mean, it's just, this picture is really small and it's hard to do business there, right? So let's look at a larger, under the microscope version of that little picture. And that little piece of curve is the image of some little piece of curve over here, right? We need to figure out what our stretching factor is. And let me just remind you, a lot of this has already been done. I already know that when you have a parametric curve, then at a given point, we can talk about the velocity vector at that point, right? And we've already talked about how you can talk about this dx vector. This dx vector is the differential of position. Keep in mind what a differential is. A differential says, I don't really know what's going on other than at this point, but based on what's going on at that point, let me assume that everything just sort of, everything proceeds linearly from there, and based on that estimate, where would I expect, in this case, my position to move to. Right, so dx is our linear estimate based on the derivative, based on the velocity vector. It's our linear estimate of our change in position. And based on what direction and how fast the curve is going at that point, sort of assume that the differential will be like this. And of course, the actual curve is a little different. Okay, so this dx idea, we've already talked about that. It goes back to chapter 12. Just a reminder that dx is v dt. Again, from chapter 12. Old news. Okay. All right, so really the new thing here is to give names to the coordinates of the dx vector. We didn't really quite get around to that previously, but I'll just make the observation that this dx vector, well, there's going to be some x coordinate. Dx seems like a reasonable thing to call that, right? I mean, the dx vector indicates the linear estimate of the change of this x vector position. The x coordinate, well, again, that's representing what's the x coordinate of the change in position. What is our estimate of the change in the x coordinate? This dx, right? It's again, old news. And then likewise dy, that's the change in the y position, and that's just the second coordinate of the dx vector. Again, old news. How to compute dx and dy. Right? I mean, that's single variable calculus. Okay. So with all of this having been built up, keep in mind my goal here is I'm counting ants, or I'm adding up mass, or what have you, right? So I'm interested in knowing how long is that little piece of curve. I want to know ds. ds is the magnitude of that dx vector. It's the length. Okay. And Pythagorean calculation, right? That's the hypotenuse of a right triangle, and no surprise, ds is speed times dt. Okay, so now let me just remind you what we were doing. We were interested in adding stuff up over this curve. We wanted to do this, and I just got through computing what that ds is. That ds, let's see, here we go. ds is v dt. The function is whatever it is. Now, of course, x is now a function of t. Right? Position is a function of time. That's the parameterization. As usual, the function, the parameterization in this case, well, would have been the change of variables function if this was a couple of days ago. The function that you're pulling back through tells you how to rewrite your integrand. So this just what I have highlighted in yellow. That says just plug in the fact that x, y, and z are now functions of t. And now, lo and behold, we've done our pullback, and what had been an integral on this curve has now been pulled back to an integral on this interval. And again, we know how to do integrals on intervals. Yeah?
I'm sorry, why is dx the magnitude of dx?
Yeah, so if you know a linear estimate of the change in your position, right? And if you want to know what's our linear estimate in the amount of distance that we've traveled, right? I mean, they're just the same thing. Yeah, that's all. Right? So keep in mind these are linear estimates, right? So they're not, I mean, the actual length of a little piece of curve, a finite little piece of curve, is definitely going to be different, right? But our estimate of that is going to be dictated by the estimate of the change in position. That's all. Yep. Mm-hmm. Anybody else? Okay. Okay. So, by the way, side note: notice that the ds here that I've computed, right? The notion of size on the curve, the notion of size on the interval are related by a stretching factor. Right? So speed is the stretching factor involved in that parameterization. That's one way to think about it. Okay. All right. Now the book makes a choice here that is, I guess, harmless. I think it's I don't know. I don't really, never really like the motivation here, but I'm going to go ahead and stick with the book's choice on this. The book, instead of developing the idea of these kinds of integrals now, the book sets this aside and goes with integrals over surfaces. I don't know. I think it's a little weird to do integrals over, do the two-dimensional version before the one-dimensional version, but it doesn't matter. It's fine. So I'm going to stick with the book's choice here. I just want to go on record that it's not me, right? This is the book's choice. So anyway, same strategy though. We have this domain over here, surface bent around in space. We want to do an integral on that surface. So again, maybe we're computing the mass of a bent sheet of metal. Maybe we're computing the number of ants crawling around on this surface. Who knows, right? Whatever. The strategy is going to be, again, to view it as an image of something and then do a pullback through that function. Okay. So this is also called a parameterization. The surface then being called a parametric surface. It's just like a parametric curve, except instead of one input giving you therefore a one-dimensional image, here we have two inputs giving us a two-dimensional image. So it's just a function from R2 to R3. Okay. All right, we'll talk about how to find such functions in a few minutes. For the moment, let's just assume that this function is given. Don't want to get bogged down in the details of how to find it yet. Again, that's coming. But for the moment, let's just assume we have it and ask, what do we do with it now that we have it? Okay. All right, so again, we want to be able to talk about, how big is that little piece of surface area, right? That being the image of this little piece of surface area. Right, so that little blue area gets stretched out by some factor to give us this green area. And the reason I want to do that is because I would like to be able to rewrite where I have, ds, that we're going to call that. I would like to be able to rewrite that in terms of that blue area, because that blue area is simple. That blue area is just du dv. Right, nothing to it. So I want to rewrite the green in terms of the blue. In order to do that, I need to know what's the stretching factor by which we stretch the blue to get the green. Okay. You know what? Actually, let me just leave that there. That wouldn't hurt anybody. In fact, let me. Yeah. Okay. We'll leave that. Okay. Okay. So it's remarkably similar computation to what we did on the previous page, and that's why I inserted this in here. This calculation here that we did in the context of curves, notice that the thing that we're interested in computing, in that case the length of that little piece of curve, is best understood by understanding that vector. That vector represents a change in position. That change in position is caused by a change in the input. And what is, given a change in the input, what is the corresponding change in position is the best way to understand the actual piece of target that I'm interested in. Okay. So we're going to do the same thing here. I'm going to look at I've already forgotten the colors. Green, okay. Oh. Okay, whatever. So that's blue. Fine. There we go. So we've got this little piece of area in the UV plane. Right? It's got some area, du dv. And I could imagine, as again, color is green. Okay, so I could imagine what happens if that gets, if I push that forward through my parameterization, I'm going to get some little piece of surface. And I'd like to compute the area of that piece of surface. Okay, now, first step is to recognize that the edges of this rectangle represent little changes. This is a change. It's not a change in t, right? Like on a parameterization of a curve. This is a change, though, in u. Right? This represents, I was here, now I'm here. U has changed by a certain amount, and v is held constant. Okay, so I'm viewing that edge as a vector representing a change in u, and I just want to compute the corresponding dx vector. What is the change in the position in the output? If you change u a little bit, that's going to change my position. It's going to change where I am on that surface by some amount. Okay, now talk about the details of how to compute that in a moment. The next thing we're going to do after that is say, well, okay, then how about if I change v a little bit? Well, if I change the input, that's going to give me a different change in my position and the output. It's going to give me that vector. And the idea then is that, well, these two vectors, between the two of them, they're not going to exactly give me the piece of surface that I'm interested in, but the parallelogram that they define is going to approximate that little piece of surface in the same way that the dx vector here approximates that little piece of curve, right? This parallelogram is going to approximate that piece of surface. So I'm going to compute ds by computing the area of that parallelogram. Does everybody see the big picture strategy there? Okay. The details, again, very, very similar. But let's see, what happened here? How do I compute, given a dx vector, how do I compute its first component? Well, its first component is just asking me about the change of one output variable, x, with respect to one input variable, t. That's a Calc 1 problem. How much does x change given a change in t? Well, there you go. Right? Likewise for dy. Well, it's the same thing here. And if I want to understand this vector, that vector says, how much does position change when I change this one input variable u? So as I move in the u direction, how much does x change? There you go, derivative. Now, of course, derivatives with respect to u. How much does y change? Well, again, it's just a partial derivative problem, right? The change in y per unit change in u is approximated by multiplying du times that partial derivative. Chapter 13. And then let's see here, color choice. I'll use dark green. Okay. Z, like that. All of these derivatives, of course, are derivatives with respect to u, because we are moving in the u direction. Okay, so very conveniently then, this vector, this purple vector, this edge of that parallelogram can be written like that. One coordinate at a time, just looking how those coordinates change with respect to the u variable. Okay, all right. And then very, very similar calculation for moving in the v direction. If you want to move in the v direction, you want to know what's the corresponding position differential. Well, this time it's going to be xv dv, because we're moving in the v direction. That doesn't quite fit on the page, does it? There we go. Okay. Is everybody on board? Okay. All right. You may not believe this. We're almost done with this calculation. Let me just remind you, our goal was to compute the area of that little parallelogram. The point being that the area of the parallelogram is our approximation of the area of that little piece of surface. How do we compute the area of a parallelogram? This goes way back to sort of early chapter 12. The area of a parallelogram in space is computed from knowing two edge vectors, right, by taking the magnitude of the cross product of those two vectors. Right, so magnitude, oh, I was using yellow. Hang on. Oh, come on. The area is the magnitude of the cross product of those two vectors. Let's see if I can get this all on. Chapter 12. Everybody remember that? Way back when, right? We've got a parallelogram. We've got the two edge vectors. Take the cross product of the two edge vectors. Take the magnitude. That gives us the area. Okay. All right. And now with just a little bit of algebraic rewriting, we're there. Recall, you can take a scalar inside of a vector like that and factor it out. And you can take this scalar and factor it out. So those scalars come on out, and inadvertently, we've got exactly what we wanted, right? So our goal, going back to here, our goal was to understand what is this green area, back to this old coloring scheme. We wanted the green area of the piece of surface viewed as being some stretching factor times this blue area du dv. So I want ds as some stretching factor times du dv. Here it is, ds, something times du dv, that stretching factor is that little formula there. And you just have to memorize this formula. And if you're doing an integral over a surface, the magnitude of the cross product of xu and xv is your area stretching factor. Okay, so... right, so there we go. That ds, we just computed that ds. It's that. Our stretching factor in there. We're interested in this integral. Don't forget that x is a function of u and v by way of the parameterization. Said differently, always pull back. Always rewrite your variables in your integral by way of the function that you're pulling back through. That's what that function does. It tells you how to rewrite your variables. Boom. Right. So altogether then, notice that one of these brand new, mysterious, floating integrals in space, we now have rewritten as a garden variety, chapter 14, double integral. Yeah? Everybody good? Okay. Turns out, we'll see this happen as the course goes on, but this vector, the xu cross xv, it turns out this comes up all the time in ways that we can't really anticipate yet. So we're going to give that a name. We're going to call it capital N. This is the book's choice of notation. It's perfectly fine. I'm going to stick with that for the rest of the course. So capital N, henceforth, xu cross xv, or the cross product of the partials of the parameterization, whatever your parameterization might be named, etc. Okay, everybody on board? Right. Now, before we actually turn the crank and actually compute some stuff with this, which we are going to do momentarily, I just want to call back to something we talked about a while ago when we very first time we did change of variables. You might recall that very first time we did change of variables, I wrote down this formula for the stretching factor. It's the Jacobian determinant. And at the time, I said, we've got a lot going on. Let's focus more on the applications, and let's kind of use the formula, and we'll talk later about how to derive that formula. Where did this Jacobian determinant come from? Right? And you guys are going to derive that for yourselves. You have all the necessary tools to do that now. And I'm going to get you started in the right direction here, okay? But you're going to derive this formula for the stretching factor for change of variables. The idea is rip off this calculation here. Okay, now in this story, this is seemingly a very different thing. We have a piece of area there. We have a piece of area, but this area over here is floating in space. And let me just remind you, right? So we have our three-dimensional axes here. So this is, every vector here has three coordinates, x, y, and z per that picture. Okay. What if you did this exact same picture, but just in 2 dimensions? I mean, literally just erase the diagonal axis. Right? Let's call that x. Let's call that y. Let's view this vector here. It no longer has 3 coordinates. Right? It now, here, let me erase that a little bit better. It no longer has 3 coordinates. It just has 2 coordinates. Right? That's the x coordinate, that's the y coordinate. How would you write those down? Well, copy from what we did here. Right? Now that you have formulas for how to compute these 2 vectors, we have this question before us. How would you compute the area of a parallelogram in 2 space? Keep in mind, we're in 2 space now. What's the formula for the area of a parallelogram in 2 space? So it's another chapter 12 flashback. Think that through. Kind of borrow the, strategically anyway, borrow the process of the algebra here. And out will come this formula that I want you guys to derive. It's exactly by that method. Give that a try. I think if nothing else, it's a great test of the extent to which you understand the argument that we made here in 3 dimensions. Okay, it's just really a 2-dimensional version of this calculation that we did in R3. Okay. All right, great exercise. If you have questions about that, come to office hours. All right, be happy to talk you through it. Help room, likewise. Other instructors. Okay, so let's do a calculation. Suppose I have a surface that's parameterized by that function. Now let me remind you, I will talk in a moment about where one gets these parameterizations from, right? We haven't talked about parametric surfaces before. How do I find a way to parameterize a surface? It's surprisingly straightforward often. So we'll get to that in a moment. So again, for the moment, we're just pretending that this is given. All right, so we have a parameterization of our surface. In our pullback domain, u and v are defined on this rectangle. Right, so u is between 0 and 2, v is between 1 and 3. Okay, so we're pulling back to a rectangle. So on this surface, I've got mass distributed by way of this density function. So depending on position, depending on x, y, and z, there's a different formula for density. And with this mass distributed per that density, I want to know what's the total amount of mass. All right? Now, the very first part of this problem is just like, the beginnings of chapter 12, mass accumulates. Total mass is the sum of a bunch of little pieces of mass. Little pieces of mass are, as they always are, density times size. Right? So that's all old news. Right? The problem, what's new here, is that this is our first time writing down from an application an integral over a surface. Right? So this mass accumulates over the surface that's been parameterized. So how do we compute a surface integral? Well, here's our formula. It's just a pullback. Good news, the formula for the pullback is always the same. Right? So ds is magnitude of capital N times du dv, or whatever your pullback parameters are. So it's very plug and chug. So here we go. First thing I want to do is compute that capital N. Keep in mind our stretching factor. Our stretching factor is the magnitude of capital N. Capital N comes from, it's the cross product of xu and xv. Those, of course, have to be computed from the parameterization. So there's a several step process. First, you've got to compute xu and xv. Then you've got to compute n, and then you've got to compute its magnitude. All right. So going through that process. Partials with respect to u, partials with respect to v. Right? No tricky curves there. Just partial derivatives. Everybody good? Cross product, chapter 12, old news. A little bit of arithmetic, right? But, not that bad. Okay. Computing the magnitude. Well, again, that's chapter 12, right? That's ancient history. So just some tedium, right? But the stretching factor, the computation of the stretching factor, know the formula, of course, and then it's just do the, turn the crank. It's just repetition. Okay. All right, so there's our stretching factor, and notice that that's what I plug in for ds. ds is our stretching factor times du dv. That's the first thing that I did there. Okay, everybody good so far? Yep.
Because you're finding the magnitude of it,
yeah.
Does it matter which way you cross it?
No, it doesn't matter. Great question. Absolutely does not matter. Yep. There will be a variation on this that we'll talk about later. It's going to be a while before we get to it, but there will be a variation where it matters, but it doesn't here. Yep. Okay, so now what about all this business? Where does that come from? Okay, well, that's our density function. Recall, density was given. So all I've done here is just rewrite that density function, x plus y plus z plus 4. Then you object and say, that's not what that looks like. What's the deal with all this u's and v's and stuff? Right? Well, this is just a two-step rewrite. Density is x plus y plus z plus 4, but those things, I'm still in the, right. Those things, what is x? X comes from the parameterization. Y comes from the parameterization, and likewise z. Everybody on board? That's just a rewrite of what density is. Density is a function of x, y, and z. X, y, and z are functions of u and v. Okay. And now it's time to turn the crank. Right? So this is a straight up garden variety section 14.2, 14.3, somewhere along in there. It's over a rectangle, right? This is an easy double integral. Okay. All right. Okay, so that's our first hands dirty calculation. Any questions? Everybody happy? Okay, so now the question that I've been sort of pushing back for the last 45 minutes. What if the parameterization's not given? I don't know how to parameterize a surface. Where does this come from, this magic parameterization of a surface that I just sort of threw in there? There is no single way to do it, but there is a way to do it that works usually. And so this is great. This is a fantastic method. I wish the book had played this up more. The book kind of undersells this, in my opinion. I think this is a really big tool for parameterizing surfaces. And it's this right here. Try to write one coordinate in terms of the others on that surface. Now, let me do a little language association. When we write one of the variable in terms of the other, when I view one variable as a function of the other variables, that means we're viewing the surface as a graph. So by viewing it as a graph, we can create, I claim, we'll see in a moment, a parameterization. So So I call this the graph parameterization. I think that's a reasonable name. Okay. All right. So, for example, how would I parameterize this plane? I want to view this plane as being, the image of some. I want x equals, y equals, and z equals, all functions of u and v. How do I get that? So, the trick, solve for one of the variables in terms of the others. I'm going to choose z, no particular reason. Once you've done that, it's all downhill from there. You're pretty much done at this point. So here's the way you finish it off. These variables that the other variables written in terms of, like x, for example, just call it u. Right? So x is u. Y, just call it v. Right? So y is v, x is u, and z, what is z? Well, don't forget z. We've just solved for z in terms of x and y. X and y are u and v. That gives me z as a function of u and v. And notice now I have exactly what I wanted. X, y, and z are functions of u and v. That is a parameterization of that surface. Very convenient. Right? Hard to beat it. Okay, so now why did I solve for z? Why didn't I solve for x or y? Doesn't matter particularly. There are some situations, depending on depending on how the surface is defined, sometimes one is maybe a little easier to work with in the subsequent calculations, right? We'll talk about that and when examples come up. But any one works. Okay, so make sure you understand what happened here. Notice you solve for, view it as a graph, solve for one of the variables as a function of the others, and then just write it down, right? Just let the input variables x and y be u and v, and it all falls into place. Okay. Okay, let's see an example. So let's consider this unit hemisphere. All right, now solve for one of the variables in terms of the others. Now do be a little careful here. We have to actually solve for one of the variables, and it has to actually be right, right, on the entire surface. So we've got to wonder, in which directions can I actually claim that this is a graph? And notice, you cannot view y as a function of x and z. It fails the vertical line test in the y direction, or the horizontal line test, whatever you want to call it. Fails the appropriate line test. Okay, so in fact, there's only one direction that this passes, and that is this way, where you're solving for z as functions of x and y, and thus you have this. And then notice I just play the usual game, right? Let x be u, let y be v, and then z is what it has to be. There's our parameterization. So that's a parameterization of that sphere. Now let's, we're not quite done. What's the range of values of u and v there? Well, we've got to think, what are the values of u and v that give me this, hemisphere? Well, the u and the v, don't forget, are the x and the y. So I want to know what are the x and y coordinates that, by way of this function, give me the points on the sphere. Well, you can see right there the x and y coordinates. Z is computed from the x and y coordinates, straight up, you might say. Right? So it's just that shadow disk down there. So this, of course, is the unit disk. And I'm going to say that's the unit disk in the UV plane, because don't forget, u and v are x and y. Yep.
How can you quickly tell if a function passes the vertical line test?
If you know what the surface looks like, and what the vertical line test says is, think about what that surface looks like, and then think about vertical lines and how do those vertical lines intersect, right? And so it requires understanding geometrically the surface. Algebra. That's the geometric way to think about, can I view this as a graph? Algebraically, the question is, can I solve correctly and completely for one of the variables in terms of the others. And, with this algebra, can I solve for z? Yes, I can. There's only one value of z that's going to make that work. And I can write down a formula for it. It's that. Yeah. Right. Okay. So here's a variation. Different kind of a parameterization. It's not terribly different, really. I like to think of this as being a twist on the graph parameterization. This is what I would like to call the spherical graph parameterization. So I am going to start this again by solving for one of the variables in terms of the others. And there it is. Rho is equal to 1. Notice that gives me, in a sort of trivial way, rho as a function of phi and theta. It's a really boring function, right? But it is I've solved for rho, right? And that's fine. So with that, again, everything just kind of falls into place. Take what you know about the variable that you've solved for and plug it in, thereby eliminating it from the formula. And now, as hoped, position is a function of two variables, and that is a parameterization. That's morally equivalent trick. Okay. Yep.
So for the previous example,
Yep.
with the hemisphere,
Yep.
what does the reparameterization tell us that we can't do?
Oh yeah. So in order to be able to compute a surface integral by this formula that we have here. Right, so this formula here takes a surface integral that I otherwise don't know how to compute, right? And it rewrites it as a double integral, a chapter 14 style double integral that I do know how to compute. The thing that makes that work, the tool that you sort of do all these computations from, is the parameterization, right? So you've got to have the parameterization in order to do that. So that is what we've achieved here, right? I took something that was not parametrized as written, and I parametrized it. Does that make sense? Okay. All right. So let's compute the area of that hemisphere by way of these. We've got two parameterizations now. By the way, notice, right? We have this what you might call rectangular graph parameterization of that hemisphere, and now here we have the spherical graph parameterization of that hemisphere. By the way, let's try to handicap this. We're going to have a little, competition here. Which calculation works out better, right? And this one here, there's a square root, but it doesn't look that bad. 2 out of the 3 expressions are trivial. That's looking really good, right? This one here, trig everywhere, right? At a glance, it's hard to figure who would be betting on the trig calculation, right? But it turns out that's the best one. It's just square roots tend to get uglier, and trig tends to simplify because of trig identities. And so remember, we talked about this before. If you have your choice between square roots and trig, with trig you have tools to work with. You have these trig identities that are very, very helpful. Square roots, not so much, right? So here's how it breaks down. If you do the rectangular calculation, there's your partials. Here's your cross product. Here's the magnitude, which, by the way, with a little simplifying, you can get down to this. That's your stretching factor. We rewrite ds as stretching factor times du dv. Here's that stretching factor. And that's looking like not such a great integral, right? On the other hand, spherical coordinates. Here's the partials. Here's the cross product. Yeah, it is getting a little uglier. But in an amazing sort of twist, when you compute the magnitude of that, look how easy. Magnitude of sine phi. This is another calculation that everyone should do once in their life. I already did mine. So y'all need to do yours. Right? So to go through this calculation, it's got a certain amount of trig in it. Right? Pythagorean identities all over the place. Take advantage. Right? But everyone should do this once. And then look how easy this integral becomes, right? So for the values of phi that we're interested in here, phi between 0 and pi over 2, this is always positive, And so I can lose the absolute values. And this is a really easy double integral. Who'd have figured? So this is a lesson I learned, the hard way, as when I was doing lots and lots and lots of these calculations as part of my undergraduate physics major, and I came to really, really enjoy, really appreciate, I'll say, the spherical graph parameterization of the sphere instead of the rectangular one. Right, so, for your consideration. Okay. Oh, I went over time. I'm sorry. I lost track of time. Okay, we'll pick up here next time. See you later.